All right, let's get started. I think it's about that time. Okay, so today we have Rafe, and I have learned about his background, so I can tell you guys about it. Okay, so Rafe got his bachelor's at University of Maryland, and then his PhD at Harvard. And then he did 2 postdocs, the first one at UT Austin, and then he moved to Oak Ridge in 1997 as a postdoc. And he stayed there to become a scientist and became a joint faculty with UTK in 2010. And since 2012, he has been the group leader for theoretical physics there. So today we're going to hear all of his expertise in a talk entitled Making the Lightest Neutron Star. So take it away.
So this is a brand new talk with only a few elements that I've used before, but hopefully it'll go well. You guys get to figure out, watch for the slides, figure out which is the slide that I was working on an hour ago.
Turn on the lights so people can see.
Yeah, that's good. Yes, because it's not astronomy if we don't have pretty pictures. Come on.
Yeah.
So I decided to take some results that we've done recently, and also this recent paper that was published about the third type of supernova that Raphael was asking about, and kind of take them together and combine them into a hopefully cogent presentation about making the lightest neutron star. And so on the left is an image, a real data image in a bunch of wavebands of the Crab pulsar. So this is supernova that exploded in 1054, left behind a remnant. In the middle of this thing, there's a rapidly rotating neutron star that is a pulsar. And the circle you see in the middle is actually the pulsar wind nebula, gas coming off of the pulsar, exciting the medium around it. The image on the right is one of our supernova simulations. And in an ideal world, our supernova simulations would look like the Crab pulsar 1,000 years later. But 1,000 years is a long time, so we're not going to get that far. But that is the ultimate objective, is that we're trying to explain all of the physics that we see in things like the Crab supernova remnant, other supernova remnants, other live supernovae that are still ongoing. That's the objective. So based on some of the questions that came up last time, talking with Fernando was talking. All right, now it doesn't want to move. Let's see. Move it out. I'm going to start with the basics because some of you might even have been astro majors as undergrads. Some of you have never seen an astro thing besides nova. So we're going to try to get everybody on the common level. And so we're going to start with the really basics, right? So really basic number one, this is a supernova. The thing on the right appeared in the sky in February 1987. It was the first supernova observed in 1987. Hence its supernova 1987A. Very simple schemes. Astronomers are not complicated people. Here. If you look at an earlier image from the same field, you can find the star that's missing, and it has this wonderful name, Sandulik minus 69 degrees 202A. Again, astronomers are not very complicated people. This was the 202nd star cataloged in a band of minus 69 degrees in declination by a guy named Sandulik. Again. Obviously, a very important star. You can see it has an arrow pointing to it, so we knew something important was going to happen to it. Actually, no, look, it's kind of like every other star in the sky, right? You don't get warning on these things that much. If someone had taken detailed observations of this star by chance, they would have said sometime in the next 50,000 to 100,000 years, that'll probably go supernova. Not necessarily the next day. Which is a lesson for all of us when we look at Betelgeuse. And I do that most nights. So, all right, so before we talk about supernovae, I have to give you some vocabulary about stars' lives, because those words will keep coming up. And again, this is the kind of stuff that some of you will know very well, and some of you won't know what anything. The most important thing to understand about stars in terms of their life cycle is the primary determiner of the fate of a star is the mass of the star. There's a long series of thought processes that go into this, but the shortest one I've ever heard, which is actually from Bob Kirshner, who's at Harvard, who says mass is destiny. That's what's going on here. So, to talk about that destiny, I'm going to introduce this graph, which is my favorite graph of all time. And when I teach this to astronomy students, do tell them, yes, I do have a favorite graph. That's the kind of person I am. I have a favorite graph, and this is it. It's called the Hertzsprung-Russell diagram. So for astronomers, it's a magnitude spectral class diagram. For the physicist, it's a luminosity in units of the sun's luminosity. Here's the sun at 1 versus the temperature of the surface of the star. And so basically a star's life gets traced out on this diagram, any star. And so, for example, here's the sun sitting where it sits on what we call the main sequence. This is where most stars spend most of their lives. Physically, what they're doing there is they're very calmly burning hydrogen and helium in the core. After they do that, they're going to go through another set of additional stages. They're going to climb the red giant branch. That's what this is. They're going to experience a helium flash, where helium is going to start being ignited in the core. Movement on the diagram is all about new burning cycles or old burning cycles being exhausted. That's what causes stars to change. So the sun burns hydrogen into helium until it has no more hydrogen in the center, climbs the red giant branch, helium ignites, comes down here to the horizontal branch, sits calmly, relatively calmly, for 100 million years or so, burning helium into carbon and oxygen. Eventually it runs out of helium in the core. Now I have a core of carbon and oxygen. On top of that core of carbon and oxygen, I have additional burning layers. There's an interface where helium is being burnt to carbon and oxygen, causing the carbon oxygen center to grow. There's a layer above that where hydrogen is burning into helium. These are very luminous. They drive luminosity up. So going up in this diagram is luminosity going up until what we become what's called an asymptotic giant branch star. As an asymptotic giant branch star, the sun is basically in the process of converting about half of its mass, 60% of its mass, into a core made of carbon and oxygen that will become a white dwarf. The other 40% of the star gets ejected back into the interstellar medium and enriches the interstellar medium. And so that's the story for the sun. For any other star similar mass, it's going to have the same features. Right? So the sun will become a white dwarf and eject a good chunk of itself back into the interstellar medium. The story is very different for a massive star. And by massive star, I mean something like 10 or 20 times the mass of the sun. Right? They're up here. This blue guy is 10 solar masses. Same diagram, same burning stages, hydrogen into helium, helium into carbon. Very different track on the diagram. For reasons that have some really good physical reasons, I'll explain some of them. But it starts out as a giant star. Giant star just means it has to have 10 times the radius of the sun. Well, as it evolves to burn helium, it becomes a supergiant star. Just means the radius is 100 times the radius of the sun. It goes from being blue, being red, so it's a blue giant, becomes a red supergiant. And in the process, the core continues to evolve. So,
if it's 10 solar masses and 10 solar radii, does that mean it's significantly less dense than the sun?
yes. That's something we'll talk about right here. So
Another question, if you said that the radius is 10 times, that means mass is 1,000 times?
no, mass is 10 times, density is lower.
Ah.
And it's not uniform density. That's a key element to remember. These things are mostly like for a 10 solar mass star, something like 80% of the mass will be concentrated in about 10% of the radius, no, about 5% of the radius. And then the envelope is very diffuse. And I'll show you a graph of what the density looks like as a function of radius in a few minutes to give you a better idea. So, but there is this general property. So this is the evolutionary history of the density and temperature in the center of the star. Stars move upwards, always upwards to the right, the higher temperature and higher density. And so, for example, here's the sun. Ignites hydrogen at a temperature of about 10 to the 7 Kelvin. Ignites helium at a temperature of about 6 10 to the 7 Kelvin. Density of about 1 million grams per cubic centimeter. One of the general trends in stellar evolution is that as you go to more massive stars, the balance between temperature and density shifts. A star like a 10 solar mass star is going to have typically for the same burning stage, so hydrogen emission, this purple line, it's going to encounter it at lower density than the sun, right? By about an order of magnitude, in fact, but higher temperature by about a factor of 3. Because they ignite at different temperatures and densities, the stars are in different configurations. An important line on this diagram is this thing here called the Fermi energy. Everybody, I hope, is familiar with the Fermi energy from statistical mechanics, right? And if the energy temperature is below the Fermi energy, then the material is degenerate. You have to worry about Fermi statistics. Can't treat things as Maxwell-Boltzmann statistics. One key thing about Fermi statistics is that the pressure is independent of temperature. And this has a very big impact when you're talking about burning, nuclear burning. Right, so the difference in central temperature and density affects the Luminosity relationship, a bunch of other things. But the thing that I want to mention here is this helium flash. If you think back to the diagram I showed you, right, the sun went up and came down, more massive stars just move horizontally. That's all because hydrogen, or in this case, helium ignition in the sun happens under high density conditions, under degenerate conditions, right up to the right of this line. So when nuclear burning starts, energy is released. When energy is released, the temperature goes up. If I have degenerate material, the pressure doesn't go up. The density doesn't therefore go down. I have a thermonuclear runaway. I have a flash. In contrast, from a more massive star, which happens under non-degenerate circumstances, nuclear reactions start, temperature goes up, the pressure goes up, the density goes down, the temperature goes down because of adiabatic expansion. There's a thermodynamic regulation. And so to the right of this line, the red line, you flash. To the left, you just kind of sizzle. Yeah.
So in part of the life cycle of the star before it's a white dwarf, the core is actually held up by electron degeneracy. Yep. Is that what I'm?
Yep.
Okay.
Yep.
Cool.
For this part of the diagram.
Yeah.
Okay, so stellar fate. For a low mass star, remember less than about 10 solar masses, I'm going to end up as a white dwarf, I said. Exactly what the composition of the white dwarf is depends on the mass. It could be just helium. For the lowest mass ones, carbon, oxygen. For most of them, there's also a possibility to be oxygen, neon, and magnesium. For more massive stars, this range on the diagram, I'm going to either form a neutron star or a black hole. Probably I'm going to have a supernova. But I want you to notice a couple of things that are important here. So the blue line is the mass of the star after helium burning. And so since this is the final mass or the mass of the remnant or whatever mass I'm talking about as a function of the initial mass of the star, this should just be a diagonal line. Except that massive stars lose mass. The sun has a solar wind. If you add up the solar wind's mass loss over the history of the sun, it's still pretty negligible. That's not true for these massive stars. These massive stars will actually lose a good fraction of their mass. In fact, for very massive stars, more than half of their mass over the course of their lifetime, before any of the higher level burning stages happen, before they can be supernovae. So this means that depending on the mass of the star, my supernova may be happening in a region with a lot of hydrogen or with no hydrogen, or in fact, maybe even with no helium, right? Because this one's actually penetrated not into the helium core, into the carbon oxygen layer. And so same physics going on the inside will show up differently on the outside because of what the star has done to itself. Okay. I should note just for fun, so there's the stellar mass loss, right? That makes this blue line bend down. The red line here is the remnant mass, so even the remnant mass is affected. So here I may get a neutron star. This will probably be a black hole. Here I might get a neutron star again because the mass loss is enough that I've transformed the star sufficiently that it won't form a black hole. All of this also depends on metallicity, which is the amount of things heavier than hydrogen and helium present in the star. So this is actually the diagram for zero metallicity. This would be first generation stars. You'll notice the blue line follows the dashed line, except for right in here. So these don't have that possibility of having a neutron star at higher mass and suddenly appear. They also have some interesting additional mechanisms for destroying themselves. Pair instability, I'll mention a little while. For stars around 150, 200 solar masses. But otherwise, especially at low mass, the diagram looks pretty similar. But there is this metallicity dependence. And it comes because heavy elements disproportionately contribute to opacity in the outer layers of the star. Iron has a whole lot more lines than hydrogen and helium does. The opacity is long, the ability for the material, for the gas to retard radiation is much higher for later stars, so they lose mass. Okay, so just one star, just as an example, this is the interior history of a 22 solar mass star. As a function of time and mass coordinate within the star. So here's the surface of the star, here's the center of the star. This is time from the end of the star's life. Inverse log. So this is 1,000,000 years before the star dies. This is about 10 million years before the star dies. Remember, the sun lives billions of years. These massive stars live millions of years. Live fast, die young. Leave a beautiful corpse. If you think a neutron star or a black hole is beautiful, most people do. All right, so let's say a few more things. So the green and red shaded regions are regions that are convectively unstable. So don't think of this as a star made out of a bunch of shells like a Russian doll. But in the regions where the green hatching is, material is moving. Essentially, the opacity is so high here that radiative energy transport can't transport energy fast enough, so convective transport kicks in. Down in these other convective regions, convection happens because the energy generation rates have a higher temperature dependence than T⁴, and that causes convection. The blue and the green are kind of more interesting. The blue and purple are kind of more interesting. The blue regions are regions where nuclear energy is being generated. You'll notice that there's this stacked layout. After hydrogen burning, there's this stacked layout, right? Here's the helium burning core, but there's the hydrogen burning shell. There's a hydrogen burning shell that persists for the rest of the life of the stars. After helium burning is exhausted in the core, there's a shell of helium burning that persists for the rest of the life of the star. And then there are other shells, carbon, oxygen, silicon. Here, 10⁻² years before the star dies. 10⁻² years is a couple days. So 10 million years of life, it's doing important things 2 days before it dies. There's a real serious acceleration of the life cycle of the star, which is why this log scale actually really works well. The purple regions are regions where you're losing a lot of energy, partly from nuclear reactions, but mostly from neutrino loss. Essentially, from this point on in the star's life, this part of the star, the light you see from the outer part of the star, is powered by these two burning sequences. Most of the luminosity is being lost in the form of neutrinos, powered by these other burning sequences. You actually have a neutrino star from the point where carbon burning starts, essentially. And the neutrino luminosity dominates the photon luminosity. Which means when Betelgeuse is getting ready to go off, a few days before it dies, our detectors are sensitive enough, we'll get a warning. Note this line here, this is the mass of the star, right? So I started out at 22 solar masses. I'm left with about 21 solar masses. When hydrogen burning is done, very rapidly, I lose about another 6 solar masses as a red supergiant during helium burning. And I'm left with a core that has iron in the center, then there's a layer of silicon, there's a layer of oxygen, there's a layer of carbon, layer of helium, layer of hydrogen. I have this set of nested dolls that I'm eventually going to run a shockwave through. All right, so now let's talk about core collapse supernova. So here is my nested set of shells: iron core, silicon layer, oxygen layer, carbon layer, helium layer, hydrogen layer. Iron core in the center is inert. There is no nuclear energy generation that comes from burning iron. In fact, burning iron takes energy out of the system. It's the peak of the density of the binding energy curve. So the star is kind of stuck. It has a tremendous need for energy generation and no way to handle it in the core. Meanwhile, silicon burning is happening at the interface between the iron core and the silicon layer. That's causing the iron core to grow. We already said the iron core is degenerate. The center of a star is degenerate in the later stages of its life. Well, for degenerate material, there's a maximum mass that you can support by degeneracy. Fundamentally, it has to do with the fact that eventually the electrons get relativistic, and relativistic electrons provide less and less pressure. And so that limit is called the Chandrasekhar mass, because Chandrasekhar is the guy who worked out the math. And I'll talk a little bit more about it later. But once the iron core gets more massive than the Chandrasekhar mass, it contracts. Contraction leads to higher densities. Higher densities lead to higher electron chemical potentials. Higher electron chemical potentials lead to a rash of electron capture. So I take electrons out of the system. I push an electron into a proton to make a neutron. Suddenly the material is more neutron rich, but also it's lost electrons that it was using for pressure support. You see where this is going, right? Really quickly, it collapses and forms this thing we call a neutron star. So the electron capture has transformed all the protons into neutrons. Almost, it'll get there eventually. Neutron star, the neutrons are actually packed closely enough together that the nuclear force acts. Right? So the separation between particles in a neutron star is similar to the separation between nucleons in a nucleus of order of Fermi. So suddenly, my collapsing core has a new form of pressure support. The inner part of the core was actually about half the core was contracting homologously altogether. The outer part of the core couldn't keep up. Keeping up would have required going faster than the speed of sound. It can't stay in sonic contact. So the inner half of the iron core contracts. Suddenly it becomes a protoneutron star. Suddenly it has a new form of pressure support, stops. The other half of the iron core doesn't know this is happening. This is what sonic contact means. Crash. If I have material collide with something else supersonically, what happens? It's the definition of shock formation. So a shock wave propagates out through the star, through the rest of the iron core, and eventually, hopefully, through the rest of the star. That shock wave is going to be my superwave, if it gets there. Turns out, if you go back, I guess it's now 30 years now. I used to say 20 years, but I'm getting older. 30 years ago, we didn't know as much about the nuclear force. We didn't know as much about nuclear matter. We thought that the material was actually more compressible. If the nuclear material is more compressible, the shock wave is stronger. Stronger shock wave can actually drive off the envelope of the star without any help. But because of laboratory measurements, essentially, we know that nuclear matter isn't that compressible. And as a result, the shock wave is weaker and it actually stalls. It goes out at about 100 to 200 kilometers. Right? The iron core is, the neutron star is about 50 kilometers at this point, and stalls. And so then the name of the game for the last 20 years is, how do I turn that stalled shock into an explosion? The answer is neutrino heating. Right? I've taken roughly one solar mass of material that used to be something the size of the Earth and is now something that's about 50 kilometers. There's a tremendous change in the gravitational binding energy. About a tenth of the rest mass is available in gravitational binding energy. Well, suddenly I have energy release in my neutron star. Energy tries to get out in every way possible. Predominantly, it will leave by the easiest way for it to leave. Right? If you think about mean free paths for every possible form of energy to leave, the longer the mean free path, the faster it gets out. Surprise, surprise, neutrinos, which don't interact with anything, have the longest mean free path. And so neutrinos are the predominant source of energy currently out of the neutron star. Even though they don't have enough, and don't have very good interactions with material. They're so bloody, many of them, carrying so much energy, that even if 1% of them deposit their energy in the matter, that's enough to power the explosion. And that's in fact what we think happens.
Is that 1% real? Do 1% of them really interact?
Yes.
It's more than I would have guessed.
Well, so the material that they're heating is at, say, 1/100th the nuclear density, so it's still pretty dense material.
Yeah, okay.
So, all right, so the story I just told you is not some random event. It's going to happen for any star that's about 10 solar masses or more massive. It's the inevitable death of those stars. So think of your favorite constellation. If it happens to be Orion, I can tell you that all the bright stars in Orion are going to die this way, except maybe the right shoulder. It's right around the borderline mass. So someday Orion will be gone, or at least vastly different. All right, so I already said this, iron core grows too massively supported by electron degeneracy pressure. Away it goes. Shock wave goes out, leaves behind a neutron star, blows the rest of the star out into the interstellar medium. In the process, it does a tremendous amount of nuclear energy generation and nuclear processing. Both the products of the star's life, this carbon shell, part of the oxygen shell, get ejected into the interstellar medium. In addition, new products that are made by the blast wave get injected in the interstellar medium. So the oxygen you're breathing, the calcium in your bones, about half of the iron in your blood, all of these things came because the star died. All right, so now what does this have to do with making the latest neutron star? I have to understand the lowest possible star that can make a neutron star. So let's talk a little bit about supernova observations first, because this will become important later. And of course, it plays into what some of the questions that were asked last time that didn't get answered. So observationally, we have two basic types of supernova, 7 subtypes. And actually, this is kind of an old number. 20 years ago, we described 7 subtypes. Now there are subtypes. When you go from having, well, 2001, there were probably a total of order 1,000 supernovae observed. We get that many in a year now. In a few years, when the Vera Rubin Observatory comes online, we'll get 10,000 a year. Particle physics people are not the only people who are going to be drowning in data. It's a good problem to have, but it is the problem. Right? So as you collect more and more of these things, you just find more and more patterns. But this basic pattern of different types of supernova holds. And so you can see, even if you're not very familiar with spectra, right, especially in the nebular phase after a year, these things are not the same. Right? And if you look carefully, you can see that there are different lines present here and here, and then at maximum and at 3 weeks. And so this leads to this dichotomous key of supernovae and the types. So the first question on the dichotomous key is there hydrogen present? Yes or no? No, it's a type 1. Yes, it's a type 2. Easy question. If it's a type 1 and there's no hydrogen, the next question is there silicon or not? Yes, silicon. Right, so here's silicon features, actually silicon and sulfur features. Then it's a type 1A. Okay. Next question, is there helium? Yes or no? Yes, helium, it's a 1B. No helium, it's a 1C. Really simple way to categorize things. Type 2s, you look at the line shapes. If it has a very narrow line, it's a type 2N for narrow. You also look at the light curve. Luminosity is a function of time. If it has kind of a flat spot and then falls off, it's a type 2 plateau. It has a plateau. If it just falls off kind of linear, although it's linear on a non-log plot, still linear, it's a type 2L. Right? Great, simple system. You understand why these things are going on. Unfortunately, it has very little to do with physics, at least the physics of the explosion. It has a lot to do with the physics of the outer layers that you're actually seeing when this happens. So on top of these types, right, observationally determined, we have theory people doing models. And the models tell us that there are, well, at least 4 supernova mechanisms now. When I was in grad school, we really talked about 2. We didn't talk about these, but they've come on since then. Thermonuclear, core collapse. I described the core collapse for you. Fernando talked about the thermonuclear last time. A couple more exotic ones. There's ones associated with long gamma ray bursts, supernova. There's 2 different mechanisms. Could be one or the other. Could be both. It's astronomy, probably both. And then there's the pair instability that I remembered several slides back. Okay. And I got to get going because I'm not talking about my work yet. Color coding here, though, lines up these mechanisms with those observational types. You see the problem? Everything's green, except for the type 1As. All of these different types are about the stellar surface. If it's lost a lot of mass, it could be a type 1b or even a 1c. It has no hydrogen left or even no helium left. But it's the same neutron star generating mechanism in the center. Blast wave doesn't care what the envelope looks like. It's going to go through it. Some of these very bright type 2Ps may be these pair instability. Some of the bright 1Cs, which are associated with long gamma ray bursts, have a separate mechanism. But you run into this basic problem that the types tell you not a lot about the mechanism, except for type 1As. They're off on their own. That'll become important in a little while. All right, now we can actually talk about neutron stars for a minute. So when we talk about mass limits for neutron stars, usually people talk about the upper mass limit, because the upper mass limit for a neutron star is very important for nuclear physics. It tells us a lot of things about the nuclear force. And the things that are just over the limit, there's not enough force to protect them against gravity. They collapse, they form a black hole. So it's also the minimum mass for a black hole. Very important piece of physics. You hear it talked about a lot. You don't hear the minimum mass for a neutron star talked about nearly so much. So one thing to think about is, well, maybe it's related to the maximum mass for a white dwarf, in the same way that the neutron star and the black hole are related. Turns out it's not. So this blue line that I drew on this diagram is the maximum observed mass of a white dwarf. So here's the number with error bars. So we'll call it 1.34, plus or minus about 0.15. Okay. So 10% limit. It's also much lower than the theoretical limit, which is the Chandrasekhar limit, which is 1.4 solar masses for Chandrasekhar for a YE of 0.5 for material that has equal numbers of neutrons and protons, like just about everything in this room that isn't iron. Right. Oxygen 16, 8 and 16, carbon 12, 6 and 12. So just for fun, these are the 2 smallest ones. This one at 1.174 solar masses is the smallest. It turns out there's a typo with the table. I went to look at this chart and tried to find more information about J153-+1559. And oddly, Google couldn't find it. So I called up Jim Latimer, well, I emailed Jim Latimer, and he said, oh yeah, there's a typo. It's 0453+1559. Should have known. It should have been obvious, right? Anyway, 1.174 solar masses plus or minus 0.004. Neutron star binaries are very well constrained. One of the things you're observing is a fast rotating clock. It's almost perfect for getting constraints on the gravity. However, some people think this one might actually be a white dwarf. The pulsar is the heavier one. So this might actually be a white dwarf. The lowest mass that we're absolutely sure is a neutron star, because it's also a pulsar, is this one, J0737 minus 3039 at 1.25 solar masses. So that's the minimum mass of a neutron star. Right. So it turns out the minimum mass of a neutron star isn't something we can get kind of from first principles about like white dwarf failure, right? It has to come from a study of both stellar evolution and supernova evolution, the two pieces of the puzzle that build it. All right, so let's talk a little bit more about that. So nominally, then you would think that the lowest mass iron core that I can make makes the lowest mass neutron star. And that would be true if you need to make an iron core to make a neutron star. And for a long time, people thought that that was the case. But in the 1980s, Ken Nemoto actually showed that you could get things that are a little lighter than the lightest iron core to collapse to form a neutron star. So for stars that are just below that 10 solar mass limit I gave you, so something like 8 to 10 solar masses, they're going to end up as an oxygen neon magnesium white dwarf. Most massive white dwarfs we know of. And under the right circumstances, if the mass of the oxygen neon magnesium part of the core plus the overlying carbon oxygen layer, which is also degenerate, the total mass of all that together breaks the Chandrasekhar mass, or approaches the Chandrasekhar mass, density gets very high. Now, for a carbon oxygen white dwarf, as Fernando told you last time, this causes carbon burning, blow up type 1a supernova. In an oxygen neon magnesium white dwarf, electron capture kicks in on neon and magnesium. Again, electron capture, just like in the iron core. Same thing happens, rapid contraction of the core. One extra fun bit, oxygen burning gets ignited once the thing starts to contract. And so as the thing contracts, oxygen burning and silicon burning turn the core into iron. So I don't start out with an iron core, but partway through the collapse, I have an iron core. I'm making a neutron star. So this shows the temperature and the density for one of these old simulations for a particular massive star. So you can see that the temperature stays pretty much constant as the density increases until suddenly this runaway collapse happens. Density comes up quickly, adiabatic collapse raises the temperature because it's too fast to radiate. And then the temperature goes up because the oxygen burning until I reach nuclear statistic equilibrium, i.e. iron. So now I have this funny thing where I have two different ways of making very low mass neutron stars. By having an iron core collapse at the beginning, or have something turn into an iron core as it goes in. Actually, the same process can happen for a free oxygen neon magnesium white dwarf that has a binary companion. Interestingly, it can get turned into a neutron star, but not make a supernova, because the supernova is about the blast wave going through the envelope. There's no envelope. Poof, a white dwarf just turned into a neutron star. Nobody knows any better. Kind of sad. All right, so which is it? The lowest mass iron core or these oxygen neon cores that make these really light objects? So the model that Nemoto presented, very sophisticated stellar evolution model, especially for its time, but it doesn't include all the physics you needed to study supernova. It doesn't include neutrinos. It doesn't include nuclear matter. And so simulations for supernovae contain all the same physics. So folks in Garking, Thomas Janke and his group, performed the first simulations of these electron capture supernovae. That's what we call the collapse of an oxygen neon magnesium core, using Nemoto's progenitor. And so this is the explosion development. So this is the radius as a function of time of different mass elements. The dark element, the dark line is the shock. So you have shock form at 0 time. When the neutron star forms, for about 100 milliseconds, it goes out slowly, and then it accelerates. And becomes a shock wave. And so this is kind of the defining characteristic of these electron capture supernovae, a very rapidly developing explosion. The reason the explosion develops rapidly, here's the density as a function of the radius. For the star, the blue one is Nemoto's model. You can see really where the core stops when the envelope begins. This model of Nemoto's for this oxygen neon magnesium core is basically a core with a very light envelope. And so the explosion goes out, essentially through this diagram goes out, till it reaches this low density material, then it has nothing to stop it. Out it goes. That's going to be different for more massive stars like this one, where the density stays higher. They retard that, and I'll talk about that in a minute. But the characteristic of these models of these electron capture supernovae is a low energy explosion that happens rapidly. So about 1/10 of the energy of a typical supernova. We use the unit beta, it's named in honor of Hans Bethe for the supernova energy, 10 to the 51 ergs, which is 10 to the 44 joules. Yeah, 10 to the 44 joules. So this is 1/10 of that, a weak supernova. This diagram shows the explosion energy as a function of time in units of 10 to the 50 ergs, so 0.1 beta, so 1 times 10 to the 51 is that 0.1 beta. Okay, so I have something that's going to look like a supernova, but a low energy supernova, to make as the other channel to make these neutron stars. The nucleosynthesis is also different than in core collapse supernovae. I'm going to go through this real fast because I'm running out of time. The key element is that whereas a core collapse supernova is going to make something like 1/10 of a solar mass of nickel, or at least 3% of a solar mass of nickel, these electron capture supernovae make a factor of 10 to 30 less than that, in part because the explosion is so weak. They also make a lot of neutron-rich material. This diagram actually shows, well, I'll skip it and talk about it later. That there's neutron-rich material, and there's also some heavy material that's made up here. These are mass numbers greater than 60, things heavier than iron. But these are all characteristics of these electron capture supernovae. That was kind of the state of the art for a while. There have been a number of improvements that have gone on in the last few years, mostly work by Sam Jones, which is why there's all these Jones et al. Papers going on. He's kind of made this a personal thing. But the upshot of all that work is that we're still left with the same picture. For our electron capture supernovae, one that goes by collapse, there's also, it turns out, a thermonuclear kind. They have the same thing. They look like subluminous type 2p supernovae with low production of nickel. So if we're looking for one of these electron capture supernovae observationally, that's what we want to find. All right. So people thought they did. Supernova 2018 ZD. Remember 1987A was the first one, and we found it in February. ZD, we have quite a few more nowadays, don't we? So they labeled 6 separate indicators that indicated to them that the particular observations they had of supernova 2018 ZD told them that it was an electron capture supernova. The progenitor they identified, circumstellar interaction and composition, explosion energy, light curve, nucleosynthesis. Whole bunch of observations they have, they're sure they have it. Turns out most of these indicators actually come back to the same things we were just talking about. The fact that I have low explosion energy and a low nickel yield. Actually, they estimate the nickel yield for this is about 3 times higher than what those models I showed you earlier said for an electron capture supernova. But they still say it's an electron capture supernova. There is a characteristic drop. So this is what makes a type 2p a p, is this plateau, and then it falls off. And ZD is the black triangles here, circles I mean. So yeah, it does fall off by more than most. And then this is the part powered by radioactive decay of nickel. So that's also low because there's not much nickel. But it's not alone. There's a bunch of others that have similar light curves. So the fact that this is the first electron capture supernova observed doesn't seem likely. If this is an electron capture supernova, we've observed a dozen at least. But they said it was the first. Well, the press release said it was the first. There's a really important, actually the paper is really good. I recommend people go read this paper and then read the press release and go, stupid press people. If there's a lesson there, don't let your results get out of your control. So ZD does show significant circumstellar interaction, which is something you would expect from electron capture supernovae, because the super AGB stars lose more mass at a faster rate than red giants, than supergiants. But actually, the calculations they do for the mass indicates that the mass loss was so high, it probably couldn't have been a super AGB star. Instead, it had to be some weird eruptive event. That can happen to either kind. Not that good evidence.
What does eruptive mean in this context?
Hold that sec, and I'll tell you in a second. I'll show you in a second. There's a more recent paper, it's actually still on the archive, it's not published, that actually redoes the spectral evolution, calculates a different distance to the star, which makes it brighter, which means it might be a red supergiant instead of a super AGB star. So they say it's a low mass iron core supernova and not an electron capture supernova. So jury's out. So what can I say that's at all intelligent about this based on the work that we actually did? So we've actually modeled, not the electron capture supernova yet, that's on our to-do list, but we have modeled these low iron core mass supernovae. So we use Chimera, that's our code. It's called Chimera because it has 3 main heads, and we know our mythology. Spectral neutrino transport, shock capturing, dynamics, and it follows the nuclear evolution, the nuclear kinetics. Plus it includes at least reasonable approximation to general relativity. There are a lot of different approximations that are called supernova models. Chimera belongs to the family of self-consistent models, i.e. all the physics goes all the way to the center. They are, of course, therefore the most expensive supernova models, but you get what you pay for. There are other classes of models that are useful for some things, leakage, parameterized models, all these other things. But if it's not a fully self-consistent model, you've made some extra approximations that you didn't need to make. So one of the unique things about Chimera compared to others is that we actually do a better job of following the nuclear composition. So this is the composition as a function of radius, bunch of elements inside the star. There's kind of different regions you can identify. This part comes from the nuclear equation of state. In this part, we assume nuclear statistical equilibrium, that the nuclear reactions, the strong and electromagnetic nuclear reactions are balanced. So then instead of following rate equations, you just have an equation like Saha equation, just the nuclear version. Then there's the silicon layer and the oxygen layer, and there you have to follow the nuclear composition in detail. You need reaction efforts. Some of our colleagues who have otherwise very good models just assume NSE everywhere, which means they're completely butchering these parts of the star, which is fine if you only care about the first few hundred milliseconds when you're still in the iron core. If you don't care about ejecta, but not a good idea. A lot of people use a small network called an alpha network. Does a reasonable job, but not great. In Chimera, we have the ability to use arbitrary networks, and arbitrary networks let us avoid some of these problems, but they come at a significant cost. And I'm not going to explain that. So a bunch of 3D models that we've run in our last series called the D series. You can think of it like version numbers, so it's version 4.0 of Chimera. And so there are 5 models on this on each of these diagrams. So this is neutrino luminosity as a function of time. This is the breakout burst when the neutron star forms. They're all very similar. In this phase, they're very different. And it literally goes with mass. The lowest mass is on the bottom, the highest mass is on the top. This is the part of the neutrino luminosity that's powered by accretion. The more massive the star, the more mass accreting on the neutrons. This is the shock wave progressed as a function of time. You'll notice that the models that are more massive, 10, 25, 15, have a long phase where they are roughly flat before they kick off. They stall for hundreds of milliseconds. This very low mass star, this 9.6 solar mass star, lightest iron core we've ever seen, actually comes off in about 100 milliseconds. Very similar time frame to the electron capture system. Yeah.
Is the shockwave bouncing back and forth there a bit? On the
So, so this is the average, this is the max, this is the min. Sometimes it fails to find the shock in certain directions, so the min can go very low. This is actually a feature I'll explain in a second. The shock finding algorithm has limitations because we're not trying to find a shock, we're trying to find the shock, and that's a little bit weirder than any shock. So this shows the diagnostic energy. Think of this as the explosion energy as a function of time. So around the time that the shock starts to move out, this 9.6 model starts to gain explosion energy and levels off at something like a little below 0.2 beta. Whereas these normal supernova models, at least the one that is producing a robust explosion, are going up towards 1. I'm not sure what this one is doing. This one didn't run long enough to tell us. So this will become relevant in a minute. This 9.6 actually includes 160 species. We're actually spending more computer time on the nuclear evolution than we are on the neutrino transport. Tony, are you there?
No.
Okay. This is where Tony gets upset because, if we're not doing neutrino transport, what are we doing? So I'm going to go over time, but I'll try not to. Because now comes the movies. So fun stuff that happens in the story of the star. So this is very early in the simulation. The collapse is just starting. I have here iron core, silicon layer, oxygen and neon layer. This piece shows the nuclear energy generation. And so you can see the silicon burning interface right here. Sorry, the oxygen burning interface on top of the silicon. Another one will show up here for silicon burning. The star is going to contract. Temperature and density are going to rise. Nuclear reaction rates are going to rise. So these burnings get enhanced. That's normal. What's interesting in this case is this one actually goes out of control and launches a shock wave out ahead of the supernova. This is actually seen in some stellar evolution models, not during collapse, but years before collapse or days before collapse. Potentially throws a big chunk of mass out, an eruptive event. This one doesn't have time to be an eruptive event. The supernova shock catches up with it before it gets chance. But that's the kind of phenomenon that produces eruptive events. Some kind of low level by the standards of a supernova explosion. And so this is now 100 milliseconds after the neutron star is formed. And that shock will propagate out, I think it's about 5,000 kilometers where it gets caught. And the peak thing that happens is when the shock finder mistakes it for the main shock. And then the main shock catches up and it doesn't matter. More fun, here's another movie. So this is going to show you, these really do work like this. This model really does work like these electron capture supernovae. One of the things that those electron capture supernovae have is this neutron-rich material that I mentioned really briefly. And so on this diagram, this part is the electron fraction. So neutron-rich is lower values, so 0.4. Proton-rich is higher values like 0.6. Most of the material in the oxygen and silicon layers close to 0.5. And then this is the entropy. And so in the entropy, eventually you'll see all of the plumes and fun stuff powered by the neutrino to the wind. So let the movie run. Now this is 10,000 kilometers. So it's going to take a minute for the explosion to get going. It's 4 pixels big right now, but it's getting bigger. If you're in the front, you can probably start to see it. If you're in the back, you have to wait about 10 more seconds. And so here I have plumes of deep red, very neutron-rich material, basically being torn off the surface of the neutron star, or from the area just above the neutron star, and thrown into the ejector by convective instability. And then behind it, the neutrino heating starts to happen. And the neutrino heating actually drives material proton-rich. Because of the mass difference between the neutron and the proton, there's a difference in the neutrino electron spectrum and the neutrino anti-electron spectrum that favors proton-rich material. And so here I'm even getting green, high YE, very high YE material that's joining the explosion later. The red is the shock wave moving out. Right? Shock wave heats, raises the entropy. And so I have this interesting configuration of neutron-rich material being followed by proton-rich material. In a normal core collapse, this doesn't happen. In a normal iron core collapse, that neutron-rich material gets buried because the explosion keeps waiting to happen. More material falls on top of the neutron star. So it's a very distinctive signature for an electron capture supernovae, but also for these very low mass iron cores. Also note the explosion is pretty spherical. All right, so we talked really briefly about that dredge up, the fact that there was neutron-rich material. Here's what the impact that has on the ejecta, the composition of the ejecta. And so this is ejecta as a function of time. Right? Material that has enough energy to overcome its gravitational potential and leave. That's the definition of ejecta. And so you can see that the first material that has that is actually very neutron-rich stuff, calcium-48, followed by neutron-rich nickel. There's a little bit of proton-rich nickel, nickel-56. Early, this is actually from the shock wave moving out through silicon. And then there's a second burst that comes later. This is actually that proton-rich material being driven out. It comes with titanium-44. You only get titanium-44 under conditions with high entropy. So I know this part is due to the neutrino-driven wind here, and this part is due to the shock wave. For a normal core collapse supernovae, the light blue line looks the same. The green line is nowhere to be found, and the red line, never. And so I get this funny configuration where I have a layer, kind of rumpled up sheet of calcium-48 on top of normal supernova objective, in this case, titanium. So they're very distinctive, and they look exactly like electron capture supernova, even though this started out with an iron core. All because the envelope was so light. The explosion gets going fast. That neutron-rich material doesn't get buried. They behave like electron capture supernova. Diagram. So remember we said, whoops, of course I did that. Remember we said one of the defining characteristics of electron capture supernovae was low nickel-56. This model does in fact have low nickel-56, less than 3 times 10 to the minus 3 solar masses. Similar to what models for electron capture supernovae have, much less than the amount of nickel-56 calculated for supernova 2018 ZV. The reason it has relatively little nickel-56 is it has lots of other nickel things. The nickel-56 is actually about 25% of the total nickel production. I'm going to skip this. If somebody asked me about calcium, I could come back to it. Maybe I can. All right. So all in all, what we found is that at least for this 9.6 solar mass model, this very light iron core, with a very light envelope, it looks like an electron capture supernova. It might as well be an electron capture supernova. It's an excellent mimic, low explosion energy, low nickel. Turns out it makes a very low mass neutron star. So here's the neutron star mass. This is baryonic mass, leveling at about 1.3 solar masses. Include the gravitational part, that's about, it'll end up being about 1.2 solar masses once the neutron star is cold. And so given the uncertainties in the modeling, you really can't tell the difference between low mass iron cores and electron capture supernova. You really can't. And so to say you've seen an electron capture supernova is presumptive. So last slide, the future. It's very likely that we have actually observed electron capture supernovae, but we can't prove it. Between the quality of observations and the quality of the models, we just can't prove it. And therefore, we can't prove whether those lightest observed neutron stars come from electron capture supernovae or from normal core collapses. So the proof will be better observations, especially if we can observe the progenitor, which happens more and more these days. Hubble's been up long enough and looked at enough parts of the sky in detail that almost always, when you get a nearby supernova, you can go find archival images and find the star, or at least find the place where the star should have been, put an upper limit on its luminosity. But we also need better modeling. And so we're going to actually do this now with Chimera. Because of the fact that Chimera can do realistic networks, we can do electron capture supernovae better than anybody's ever done. I would argue that the 9.6 model we did with the large network, at least from the point of view of its compositional following, is the best supernova model anybody's ever done. It better be, it was one of the most expensive. So we have the project started on this. Maybe 2 years from now, we can actually tell you something. Those of you that are still here. And with that, I'm going to stop and take a breath.
All right, thank you so much. All right, do we have questions from the students?
So you said something about neutron stars being held up by nuclear forces.
Yep.
I thought they were held up by degeneracy pressure, similar to white dwarfs, but with more massive particles.
So if you calculate, Yuri's had all the questions I was trying to answer at the beginning part. Okay. So if you take the same relations that you derive for pressure for electrons in a liquid, change the mass to the mass of the neutron.
Yeah.
What you would get is a stable neutron star that's about 3 kilometers in size. Real neutron stars are about 15 kilometers in size, 12 kilometers in size. So there's some other contribution that comes first, and it's the nuclear force. Essentially, if you think about the nuclear, well, you guys probably don't know this, but nuclear potential looks kind of like, let's see if I get this right. There's a repulsive core, and then it does this. And so nuclei really like to sit here with that kind of separation at like 1.3 Fermi from each other. And so the pressure is intense when you try to compact them more than that. And so that contributes more than the neutron degeneracy pressure. But in astronomy 151, we often say neutron degeneracy pressure because they're not going to get this. And the neutron degeneracy pressure is close. But it is a contribution. Make sense?
Other questions from students?
Is there a way to get more sophisticated modeling without it being more expensive? Like, well, when the Vera Rubin telescope launches, and you get those like 10,000 supernova per year, you're seeing, will that help, reduce the cost of?
No. So the models will be the same, but what that'll mean is that there's more things we can find that if, instead of they make an observation, I calculate a model. I calculate a model, we do a database search to find something that looks like it. And the database is bigger and bigger and bigger. That's the hope for on that side. Of course, with that kind of event rate, you need follow-up, you need spectra to really do a good job. Somebody has to decide that one's important. Does this sound familiar? The particle physics people?
Well, we don't have nearly as many new things as you do. I was just,
Well,
we
when
would
you do,
love
it's
to be in a
important though, right?
situation where we were like, what is that?
Yes, no, serendipity,
Crossing our fingers.
the worst thing in the world about astronomy is you can't make your own experiment. You're sitting there waiting to see what happens. The best thing about astronomy is that Mother Nature is way more creative than we are. So she gives us things that we would never ask for. So it goes both ways.
Other questions?
Of course, there is the hope of a galactic supernova, in which case we'd have all 3 messengers.
Yeah, no, yes, we would have neutrinos, we would have gravitational waves, and the neutrinos and gravitational waves are important because their signal is coming from the vicinity of the neutron star. You don't have to worry about, is it a helium environment or a hydrogen on the outside? Is it type 2p or a type 1b? How do I diagnose all the other pieces buried beneath 20 solar masses of hydrogen? So those would be great, but it does have to happen in our galaxy. So it reminds me of a joke though. So as a modeler of supernovae, what do you think the first thing I should do after somebody calls me and says there was a galactic supernova?
Find a model that matches it.
No, the first thing you do is update your resume. Because suddenly what you do is going to become very important. Then go find a good model. Don't sleep for the next 3 years, running as many things as you can think of. Beg for all of the biggest computer in the world because you need it today. But after you get your CV updated.
All right, I have a stupid question for you. Is Chimera a backronym? And if so, what does it stand for?
No, it's just it's a 3-headed monster.
Okay, but you put it in all caps, so I felt like maybe you had done
It's supposed to be all small caps, but I get lazy
Okay, all
because
right.
it's a code name.
Tova, that's because he graduated from Harvard.
Oh, yeah. The MIT guy's gonna lecture the Harvard guy on grammar. We have fun. So one last thing I want to say, this image that's in the background, nobody asked me about it, but it's fun. So this is a recreation of the night sky in the year 1006 from the south coast of Turkey. And this is roughly what the supernova 1006 would have looked like, casting a shadow. about a quarter of the brightness of the full moon. So going back to Tony's comment about a galactic supernova, there's a lot of fun to be had. So, any other questions?
Oh, yeah. Oh, Oh, no, okay, when you had that tree diagram showing classifications of supernova, you didn't discuss type 2B.
So,
yeah.
So let me go back to this, because this is. So. Remember I said Mother Nature has a way of giving us things we didn't ask for? So supernova A7A is the brightest supernova that has happened relative in our lifetime. Well, not in our galaxy, but in a satellite galaxy, so nearby. It turned out to be a star that we didn't think could explode. All kinds of weird stuff. It has this weird hourglass shape. There is nothing that met our expectations. This actually follows the general rule of supernovae. The closer it is, the weirder it is. So the second closest supernova is supernova 93J. Supernova 93J, when it was first detected, was a type 2. After about 2 weeks, it turned into a 1B. Think about how that could happen. How could I be hydrogen rich for the first 2 weeks and then helium rich?
Burn through all hydrogen?
On the right track. So it's worth thinking, you guys don't know this, but it's worth, so as the supernova expands, not the model, the real thing expands, right? Densities go down. So the photosphere, the light, the place you're seeing when you see the light is receding into the star. And so 93J, the star that became 93J had a thin layer of hydrogen that was visible as the photosphere for the first 2 weeks. And then you got into the helium layer. So it was a transitional phase, right? But also a good demonstration that of this connection between type 2s and 1Bs.
Did you stop seeing the hydrogen entirely?
Yeah.
In that? Okay.
Well, so it expands, it cools, it gets neutral.
Okay, yeah, okay.
So that's the story of supernova 93J. We think 93J actually lost its hydrogen to a companion, not because of stellar evolution, not because of its own winds, but because it had a companion that stole mass. Another additional complication, just for fun. Any other questions?
When's Beetlejuice gonna do its thing?
Hopefully Monday, because I need the weekend. Anytime, and anytime could be the next 50,000 years.
Okay.
There was a big deal recently because Betelgeuse got dimmer. And therefore, some people, including some people who should know better, said, oh, something's happening with Betelgeuse. Maybe it's starting to explode. No, what happened was it threw out a bunch of mass. Actually, if you look at an image of Betelgeuse, Betelgeuse is not a sphere. It's kind of lumpy. There's convection going on that reaches the surface. It looks more like cauliflower, we think, than like a sphere. And so it threw off one of the cauliflower blooms. As that bloom went out into space, it cooled. The metals in it formed dust. Dust blocks optical light. And so suddenly Betelgeuse, the lower half of Betelgeuse, actually, if you look closely, got dimmer. So this is a baby version of one of those eruptive events. The big eruptive events have to be powered by the center, but you can have small events like this that happen powered by essentially the convective layers. So false alarm, Betelgeuse is not going, although it may, the core actually knows very little about what's going on the surface. Because essentially the carbon layers and the layers inside of that are this neutrino star. And so the behavior of the surface layers is governed by the hydrogen and helium burning shells. It doesn't care very much about the core, and the core doesn't care very much about it. So the neutrino luminosity would tell us things. The Betelgeuse isn't bright enough for us to see yet, but it will get brighter. We should see it about a half a day to a day before, if all the telescopes are in neutrinos. If all the telescopes are working that day, if our models are right, what else could go wrong? Yeah, that's enough.
How long would it take to see a neutrino from Betelgeuse at the current rate? Like, I'm sure you couldn't tell it was from it, but I'm just curious, like, how far are we away from that rate?
I'd have to look at the numbers.
So
Hyper K is not enough.
I see that. I see the question.
Although I think hyper-K gives us an extra day.
Oh.
Something like that. I'd have to find the right number. Yeah, that's the idea. Any other questions? Thank you for your attention. Thank you for laughing at my jokes.
Yeah. All right, thank you so much. That was a great. All right, and we got so many new folks today, too.
I don't think we can follow that up.
Yeah,
No, I don't want to go anywhere.
You don't have
It
to.
should be at least that joke dance. That's
I'm
my.
It should be at least that dense in intentional jokes. The unintentional jokes,
Joe, I
those
need
are
to show you
bonuses.
something. I sent it. This is what I sent to our Skype chat
All
earlier.
right, bye all.